Hey there. In the absence of having me there to teach class today, I have recorded a video, which is the first half of the slide set that's in Veracross on um, intermolecular forces, the relationship between what intermolecular forces are, the relationship between polarity and intermolecular forces, and et cetera. And if you're the sort of person who likes to download these slides and go through them and take notes before we've done them in class, these slides have been reworked a little from what's in Veracross, but I'm hoping by the time you actually get to class and see this, I will have replaced those slides with the newer version. Okay, so we want to talk about intermolecular forces. Before we do that, let's just remind ourselves about polarity. A dipole moment, which just really means a polar bond or a polar molecule. Um, Dipoles are a measure of how equally or unequally the electrons are shared in a bond. If you have a diatomic molecule, and I'm going to illustrate this for you on the next slide. If you have a diatomic molecule, um, then the polarity of the bond, because if you only have two atoms in a molecule, you've only got one bond. So the polarity of the bond is going to be the same as the polarity of the molecule. So what I've got here actually is just a chunk of the key to the homework you guys did, and I've circled in here all the diatomic molecules, that is, molecules that contain two atoms. If the atoms are the same thing, like an N2O2 Cl2 H2, then that's a nonpolar bond, and because that's the only bond in the molecule, it's a nonpolar molecule. If the atoms are different from each other, as in HF or CO, then that's a polar bond, and therefore, since it's the only bond in the molecule, then the molecule itself is going to be polar. As we talked about the other day in class, and we were kind of looking at slides with electrostatic potential maps on them, I was also showing some um, some molecular models in my hand in class. If a molecule's got more than two atoms, then whether or not the molecule itself is polar is going to depend not only on the polarity of the individual bonds, but also the shape of the molecule. And we talked about thinking about a bond dipole as a vector quantity and the overall dipole for the molecule being the vector sum. We also talked about the concept of the three-dimensional tug of war, or the sort of, does it have a sidedness? Does it have one side of the molecule that's one color, another side of the molecule that's another color? So we've talked about different ways to think about that. If there are no bond dipoles, then it's going to be a nonpolar molecule, and if the bond dipoles cancel, it's going to be a nonpolar molecule. But if the bond dipoles do not cancel themselves, if they add up to something, and we would refer to that as an asymmetric molecule, then they have a net dipole, which is the vector sum of their individual dipoles. And then it's important just to remember that molecules may look symmetrical in two dimensions when we draw a Lewis structure, but they may not be symmetrical in three dimensions. And the reverse can be true as well. If we draw sulfur trioxide just as a Lewis structure with north, east, west, and south, it looks unsymmetrical, but it actually is symmetrical. But the example I wanted to give here is what's called dichloromethane. And there are a couple different Lewis structures here. They're missing the non-bonding electrons. I got these off the internet, and they just didn't have non-bonding electrons drawn. But if you were to draw CH2Cl2, it would seem like you could potentially draw two different molecules, one in which the chlorines are adjacent to each other and the hydrogens are adjacent to each other, one in which the chlorines are opposite each other and the hydrogens are opposite each other. Those actually turn out to be the same molecule, because in three dimensions, it actually looks like the ball and stick model over here. And you can see there's definitely a hydrogen white side to it and a chlorine green side to it that makes it non-symmetrical, and therefore it's polar. Okay, so let's talk about intermolecular forces, and one of the simplest ways to think about what's the importance of intermolecular forces is states of matter. So you've got gases, you've got liquids, and you've got solids, and the question is, what is going to make a substance be a gas or a liquid or a solid under particular conditions um, of temperature and pressure? And the answer to that is the strength of the attractive forces between molecules. So we talked about a couple of units ago that in a gas, the attractive forces are negligible compared to the kinetic energy. In a liquid, the attractive forces are comparable to the kinetic energy. And then in a solid, the attractive forces are not significant compared to, I mean, the attractive forces are much stronger than the effect of the kinetic energy. And so what it really boils down to is what the strength of the intermolecular forces are. So let's talk about intermolecular forces and what they are. Intermolecular forces, and we often use just the initials IMF to abbreviate intermolecular forces. They are attractive. They're not bonds within molecules. They are attractive forces between molecules. And the strength of those attractions between molecules, between particles, is reflected, as we said, in properties like boiling points and freezing points. Now, it's important to understand that intermolecular forces are much weaker than covalent, ionic, or metallic bonds. And you may, if you had biology last year or you're in biology right now, we talk about hydrogen bonding, which occurs between water molecules. It also occurs between the base pairs in DNA. And we talk about, quote unquote, unzipping hydrogen bonds. That's because hydrogen bonds are a kind of intermolecular force. And although they have significant strength and influence the properties of these substances, they're easier to pull apart than covalent bonds. And one way to think about this, here are two hydrogen chloride molecules. There's a covalent bond between hydrogen and chlorine in each molecule, but here is an intermolecular force between one hydrogen chloride molecule and another hydrogen chloride molecule. And you can think of this, if this isn't too strange for you, by analogy. You've got two people who sit next to each other in class. They're very dear friends. And so you can think of their dear friendship as being the intermolecular force between them. It would be relatively easy to have those two people stand up and move away from each other. Whereas to try and like rip a person's hand off of their body, which would be like a covalent bond, is a more difficult thing to do. So intermolecular forces, while they are significant, are not as strong as covalent bonds. Okay, well, the fundamental principle behind all intermolecular forces is that opposites attract. And so we know from talking about ionic compounds that a positive charge will be attracted to a negative charge, and that's how ionic compounds form crystal lattices. But then we've been talking about the fact that polar compounds have partial positive charges on one end and partial negative charges on the other end, and a partial positive charge is also going to be attracted to a partial negative charge. So that's really the basis behind intermolecular forces. Okay, the first intermolecular force we're going to look at is called a dispersion force, and this is where when I'm through talking about dispersion forces, this is where I'm going to stop this video. Dispersion forces are forces that are exhibited by all compounds. Now, we've just gotten through talking about the fact that some compounds are polar and some compounds are not polar, and that the basis for intermolecular forces is partial positive charges being attracted to partial negative charges. But what if you've got a nonpolar molecule or a nonpolar atom? How do those molecules wind up being attracted to each other? It's through what we call dispersion forces. And so these slides just sort of make the point. I don't even want to go through these bullet points. I'm just going to go to the next slide, which makes the point just using helium atoms. And these are called dispersion forces. They're also called London forces, after the name of the man who first proposed their existence. Okay, so we're going to do this with helium atoms. You've got two helium atoms here. In the nucleus, there are two protons and two neutrons. But in the electron cloud, each helium atom has two electrons. And you can see that in atom A, the electrons are evenly distributed. But at this moment in atom B, the electrons are not evenly distributed. In this moment in time, they happen to both be on the left side of the atom. Okay. What that does is creates a temporary dipole in the molecule, in the atom, so that while this atom has no temporary dipole, the one in which the electrons are not equally distributed has a temporary dipole. And so there's a partially negative side over here where the two electrons are. There's a partially positive side over here where there are no electrons. What that does is has the effect of creating, just like one magnet being used to, just like the idea of using magnets to pick up a chain of paper clips, that will induce a temporary dipole in the neighboring atom. And so what you get is this temporary situation where just out of the statistical probability of the moment that one atom has an unequal distribution of its electrons, that will induce an unequal distribution in the next atom and the next atom. It's a little bit like thinking about maybe a little breeze blowing over a wheat field, and it's pushing over the stalks, and then the stalks are just a little bit, and then the stalks are pushing over other stalks, and the stalks are pushing over other stalks. This creates these temporary dipoles that will attract these molecules to each other. So all substances exhibit London dispersion forces, but they are the only intermolecular force that is displayed between nonpolar molecules. So if you have a nonpolar molecule, and in the slides we were looking at the other day in class, the example that we had of a nonpolar molecule where I had the electrostatic potential map was carbon dioxide. The only intermolecular forces between carbon dioxide molecules are dispersion forces. Well, it turns out that you can have molecules that have relatively weak dispersion forces, and you can have molecules that have relatively strong dispersion forces. And what causes that to be the case? This has to do with what we call polarizability, or the ability to distort the electron cloud. It turns out that helium is kind of a bad example, because helium is a very tiny atom. It's not all that easy to distort the electron cloud in helium, which is why helium basically is not even a solid at 0 kelvins. So let's think of some bigger atoms and some bigger molecules. The bigger the electron cloud, the more it can be distorted, the more polarizable we consider it to be. We can kind of think about it as sort of the squishiness of the electron cloud. In general, the polarizability is going to increase with the number of electrons, which means that the dispersion forces increase with increasing molar mass. So I've got a slide here that's a little bit difficult to explain, but let me see if I can do a decent job. The maroon things here are the noble gases in periods 2, 3, 4, and 5, neon, argon, krypton, and xenon. And this is their boiling points. And while these are all gases at room temperature, because room temperature in kelvins, as you'll recall, is in the 290s, their boiling points do increase from 27 kelvins for neon up to 166 kelvins for xenon. What's more interesting to me is the diatomic halogens, fluorine, chlorine, bromine, and iodine. So that fluorine and chlorine are gases at room temperature, but as you get up to bromine, which has a higher molar mass, more distortable electron cloud, stronger dispersion forces, the melting point, the boiling point actually is above room temperature, 332 kelvins, which is about 60 degrees Celsius. And so bromine is a liquid at room temperature, and iodine, which boils at 458 kelvins, almost nearly 200 degrees Celsius, is actually a solid at room temperature. So this is just making the point that as the molar mass goes up, the size of the electron cloud goes up, the polarizability or distortability of the electron cloud goes up, the strength of the intermolecular forces goes up. This is the last slide, and this is just a little question for you to ask yourself. I've got two compounds here. This is called carbon tetrabromide. If you drew this, it would be a tetrahedral compound with carbon in the middle and 4 bromines around it. This is dodecane, which has 12 carbons all linked together, and then they're surrounded by hydrogens. They're both not completely nonpolar. Carbon tetrabromide has only 5 atoms, whereas dodecane has 38 atoms. On the flip side, dodecane has a molar mass of 170 grams per mole, whereas carbon tetrabromide has a molar mass of 332 grams per mole. So which do you think has the higher melting point? Is the deciding factor number of atoms, or is the deciding factor molar mass? Well, you can pause this for a second if you want and think about it, but here comes the answer. The answer is that carbon tetrabromide melts at a much higher temperature than dodecane. Dodecane is in fact a liquid at room temperature. Now, if you made this a little bit longer, C14, C15, now you're getting up to where it's like paraffin wax and it will solidify. But dodecane is a liquid at room temperature, whereas carbon tetrabromide is a solid at room temperature. So it's actually the molar mass, because this is a much larger, even though it's only got 5 atoms, these bromine atoms are huge. And so it's very sort of polarizable, very squishy, increases the strength of its dispersion forces, makes them much stronger than the dispersion forces in dodecane. So that's where I'm going to cut this off. I don't, as I'm recording this now, there is no homework assignment associated with this. There will be another one of these videos for the next class, and then a homework assignment that goes with both of them. Thanks for watching.